Good morning everyone and welcome to the fourth in the Limit State webinar series for 2015. I'm Tom Pritchard, your host for today, and I'll be introducing you to our speakers shortly and also rounding up at the end. Today's webinar is Introduction to Limit State Geo, and it will introduce you to the technology behind our geotechnical analysis software Limit State Geo, and also demonstrate how the software can be used for a number of different situations. The main section of the webinar will run until about 10 o'clock UK time and will include 5 or 10 minutes at the end for questions. These can be posted at any time during the webinar via the chat functionality that's present in the interface in front of you. As always, we do try to answer as many questions as we can, but sometimes this isn't always possible. We're sorry in advance if we're unable to get round to yours. We will, however, try to follow up on any unanswered questions after the webinar has finished. We have a mixed audience today. Some of you will have used Limit State Geo before, some of you will be quite new to it. If you do have some specific questions regarding the software which you think might require some consideration or time to answer, then you're more than welcome to contact us outside of the webinar via info@limitstate.com, and we'll be happy to answer these in detail for you. So without further delay, our speaker today is Dr. Colin Smith, who is the Limit State Geo Product Manager, and I'll now pass you over to him.
Thank you, Tom. So good morning to those of you in the European time zone, and good afternoon or evening for those of you joining us elsewhere in the world. As Tom has mentioned, my aim today is to give you an introduction to the main features of Limit State Geo, how to use it, and what it can do. To this end, I'll primarily be using the software directly to illustrate the key points, but we'll make use of a few slides at the beginning and end for an introduction and summary. I think it's useful to first give some context to the software and to the company Limit State. Limit State, or the University of Sheffield rather, has been conducting research into limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now. And the company Limit State was spun out from the University of Sheffield in 2006 with the aim of making this research available to industry. Now, of course, industry users want not only powerful tools, but also ease of use and support, which is what Limit State provides. It also has a sophisticated testing systems in place, which means every time the software is updated or changed, almost 1,000 tests are automatically run to ensure the software carries on doing what it's supposed to do. Now, as I've said, Limit State focuses on tools for limit state or ultimate limit state analysis. To put this into context into other currently available software, on the one hand, on the top left of this diagram, we have generally easy to use software and spreadsheets that are based generally on conventional hand calculation type methods. And these can deal with specific problem types. On the other hand, down on this bottom right, we have a more complex finite element software. These can model any problem geometry and complex soil behavior, but often can be quite difficult to use. Between these two, there's a gap, and this is where we feel limit or computational limit analysis sits, or rigid plastic analysis. This type of method provides the ease and use of traditional software. You only need a few parameters such as cohesion, friction, and unit weight, but it gives you the flexibility of dealing with any geometry that you get from finite elements. This is primarily what Limit State focuses on. Now, this sort of approach can deal with geotechnical problems. It can also deal with other engineering problems such as masonry arch bridge analysis and concrete slab analysis. All of these can be cast in a rigid plastic form and use computational limit analysis. In terms of the geotechnical analysis, this ability to find collapse loads can be applied to a whole range of problems. We can deal with any geometry, so as you can see from the slide here, we can model footings, retaining walls, slopes, combined problems, soil structure interaction problems, where we can find the collapse load and the collapse mechanism for any of these problem types. And similar flexibility can be found in other limit state products. present, we have limit state ring, limit state geo, which is the subject of today's webinar, and limit state slab for concrete slab analysis. If you've not used our software before, you may not be aware of how easy to use it is, and we feel this is one of the attractions, as well as its powerful ability to deal with, to generate collapse modes for any geometry. And this has led to it being adopted by a wide range of companies across the world. Anyway, that's enough introduction. Let's try out the software and just show you how to use it, what it can be used for. So I'm now going to change to software. So when we start it up, this is the window that we see. This is a standard layout. You can see that we have a number of buttons across the top, down the left-hand side, something called a Materials Explorer on the left, and a Property Editor on the right. I'll describe how we use these as we go along. If we want to set up a new problem, we just click top left button here, New, and we get this little window which allows you to either generate an empty project where you can draw your own geometry, but the software also comes with a whole set of built-in wizards which can rapidly generate standard geometries, which can then be modified later. So we'll start with a simple footing. This then brings up the wizard, and you can put in a number of properties. So here we can put a description of the problem, which we'll omit. Here we can generate the geometry, so the width of the footing, size of the soil body, and so on. We'll stick with the defaults here. Then we can define the material properties. Again, we'll stick with the defaults, but at the moment we're specifying an undrained shear strength of 50, a unit weight of 20, and we're declaring this material is, as set here, behaves always undrained. We can then set the material properties for the footing. We're just going to make it a rigid, weightless material, and we can also specify the interface properties between the soil and the footing. So we're setting these values here, which basically say that on the interface we have half the friction and half the cohesion of the adjacent soil body. We then specify a load. Default here is 1. I'm going to set that to 100. So it's 100 kilonewton per meter load. All the analysis is in plane strain, so this is per unit length. And we can then set up partial factors, which I'll skip for a moment. We'll come back to that later. And some further information about the analysis type. We're going to use what's called factor load, which is finding the margin of safety on the load applied to this footing, and nodal density, which governs the accuracy of the solution. We'll come back to that later again. So there's our geometry all set up, and to solve, you simply press the solve button up there, and the software rapidly homes in on the collapse mechanism. If you're familiar with bearing capacity on clays, that's very close to the classical Prandtl collapse mechanism, and we can animate just to give us an idea of what's happening in that particular mechanism. Key value here is what we call the adequacy on load, 2.601, and what that means is that that load of 100 which we applied to the surface here, we need to multiply that by 2.6 in order to generate collapse. So that's the meaning of that particular number. Now, that's a fairly standard problem, but of course it's often the non-standard problems that cause issues. So what happens, for example, if we have a slope on one side of this foundation? So I can click on this boundary condition here. Anything I click on in this window, its properties appear on the top right. And we have a support type here called fixed. I'm going to set that to free, and then I can click a point there, drag it along, and give us something like a slope there. So then if I click solve, the software will now find a new collapse mechanism, and it's very different from the previous one. Clearly it's going to slide down towards a slope, and we now have an adequacy factor of 1.882, which means that that foundation can only take a load 1.8 times bigger than we specified, rather than the 2.6 that we had before. I'll just undo that. So we have an undo button here, so I can just undo and revert that back there. We can also, for example, supposing you've got a scenario where you've got a foundation and someone digs a trench next to it. There's a trench, so I'll just generate that, click delete, and we get a similar failure type mechanism. And here we've now come down to 1.2, so we've only got a margin of safety of 1.28 now on that load, which is what we need to multiply it by to cause collapse. But it's very easy to do what-if type calculations in this. So suppose you've got a trench there, and, well, hypothetically we think, could we construct a wall next to it? It's not a very elegant wall there, so I'll make that out of concrete. So I have material properties over here on the left. These are standard things, so this concrete just basically has a very high shear strength and a unit weight. I can drag and drop that, put that in place there, so I've now got a wall there, and we can see whether that, let me just see what's happened here. Right, I think I've just set the geometry slightly too far down, so we'll try that again. Let's put a smaller wall in place. Put the concrete there, and then run the analysis. And the presence of that rather strange looking wall has improved the adequacy factor on that load. So it's very easy to do what-if type calculations, modify the geometry slightly, change material properties, and get a feel for what's controlling the problem, what are the key issues in the problem. Now I'm going to revert back to the original problem, so just keep clicking undo until we get back to that. And just to go a bit further into the meaning of this adequacy factor, we've got an answer of 2.6 here, which means, as I said before, we have to multiply this load by 2.6 to cause collapse. So to clarify that, supposing I change that load, instead of it being 100, I change it to 200, so that's a defined load there. What we should find is now we've got a margin of safety of just 1.3, and that indeed is what the software produces, exactly the same collapse mechanism, and now it's telling us we would need to multiply that load by 1.3 to cause collapse. The alternative way of using this setup is, supposing we just wanted to know what the bearing capacity was, if we just set that to a unit value, that load to a unit value, then whatever answer we get will be the bearing capacity in terms of load. So here it's now giving us a number of 260. So basically we have to multiply that unit load by 260 to give us collapse. So we can use the software in two different ways, either put in the load, the design loads, or we can simply put a unit load in and get the software to tell us what the bearing capacity is. Now, before I go further with software, you'll have seen that when we run this analysis, we get various points appearing on the screen and these slip lines gradually evolving to a certain state. So I think at this stage it's useful to quickly go back to the slides and just explain how the software works, what it's actually doing. So the key underpinning the software is a relatively new numerical technique called discontinuity layout optimization, or DLO. That was an outcome of a 5-year research program at University of Sheffield, and the core method was published in the Proceedings of the Royal Society in 2007. And it basically works like this. We have a domain here, it's a very simple domain. We have a block of soil, with a load at the top, fixed boundaries to the left and to the base. Instead of discretizing it into elements, as in the finite element method, we actually populate it with a series of nodes. So here we've got a 4x3 grid of nodes, that's 12 nodes. And we connect every node to every other node with a potential slip line. So in this case, I think we have 12 times 11 divided by 2, so that's 66 potential slip lines in this problem. And then we can cast that as a linear optimization problem, feed that into a very powerful linear optimizer, And what that will do is it will select out of those 66 slip lines the key slip lines that give you collapse, essentially that give you the mechanism that dissipates the least energy. And in this case, out of those 66, we can pick out the 6 or 7 slip lines that give you the key mechanism, this is a critical one in that case. Now, this, of course, is a very simple case with just 12 nodes. Normally, we're modeling with 500, 1,000, 2,000, 4,000 nodes. So with 1,000 nodes, you're looking at around about 1 million potential slip lines, and out of those, the software will pick the critical set. So the more nodes you have, the more slip lines, the closer the software can get to the true collapse mechanism. But generally, when you've got 1,000, 2,000 nodes, you're going to get very close in most cases. Once we solve the problem, the software connects all these slip lines together to identify the solid blocks that are in between the lines, and then animates it, and that's just to help interpretation of the problem afterwards. So, looking at Prandtl problems, well, this is the one we've just looked at with the software. This is a Prandtl punch problem, and if we look at the numbers closely, we find that we get within about 1% of the exact solution, which is 2 plus pi multiplied by the unchanged shear strength, in about 1 second. And the nice thing about this analysis method is that it inherently deals with singularities. What you find often with collapse mechanisms is you get these kind of fan zones that appear where lots of slip lines are meeting at a point, and that is a mathematical singularity where basically you have many stress states at one geometrical point. Finite elements find this quite difficult to deal with. You have to design the mesh carefully, use mesh refinement. With this software approach, the singularity is identified without difficulty. There's no extra programming done. It's just inherent in the method. You can use the software to map out yield surfaces for foundations. So here we're mapping out a VH surface for a foundation. The graph on the right, the blue line is the theoretical results. The red dots are the software results, and we get a very close match. So you can set it up to explore a whole range of different problems. Now, being a relatively numerical method, obviously you want to be sure that it actually does what it says on the tin and gives you the accurate answers. So as I said earlier, we have a lot of tests that are run automatically every time the software is modified. Many of these are verifications against closed-form solutions that are available in the literature. And over 100 of these are available on the website that you can look at. This is just one example of an undrained anchor. So this is an uplift of an anchor, and we have a benchmark of 17.97. In the literature, software gives you an answer of 18.1 for a relatively low number of nodes, and so we're within 1%, which is acceptable for most purposes. Okay, so what I'm going to do now is, having gone through that introduction or explanation of how the software works, just have a look at this problem again, but this time we're going to use sand. So this soil at the moment, if I click on here, has been modelled. Its properties appear here. It's basically been modelled as a soil of strength 50, unit weight 20, and it always behaves in an undrained manner. Well, we have a lot of materials defined on the left here. You can define your own materials, which are basically these materials that were defined by the wizard, but you can define them yourself. And there's some built-in ones just for quick what-if type calculations. We've got one here called loose sand. Has a shear strength of 30, unit weight of 14, dry, saturated weight of 19. I can simply drag and drop that onto there, replace the material, and now the soil there is a sand. This interface here, I'm going to change to a frictionless interface, drop that on. So now we have a smooth footing sitting on sand. If I click solve, you'll see we've got a very different collapse mechanism, which is what you'd expect for a foundation on sand. And what you'll also see here is that when I've animated it, that some of these blocks appear to come apart. Now this is perfectly correct. This software uses rigorous plasticity analysis, and when we model frictional materials, that friction is modeled as dilation. So in the animation you'll see that dilation happening. As the material slides, it will actually dilate and come apart. Now, as I mentioned earlier with the DLO method, the accuracy depends on the number of nodes used. I can click here, Analyze Preview Nodes. There are the number of nodes that we're using at the moment, which is 500. I can change that nodal density using this setting up here. So if I click anywhere on the blank area on this screen on the right, we get the property editor for the project. So that gives us some high-level definitions, one of which is the number of nodes to be used. And I can change to a fine nodal density, which gives me 1,000 nodes. If I preview the nodes, you'll see that we've got a lot more nodes in there. And if I solve, you'll see that I get a more refined collapse mechanism, and I get a result here. This is a multiplier in the load, which I think is set to 1 of 65. Before we had 71. So the accuracy has gone up. We've come down a load, and then if I can also set this to say very fine, we now got 2,000, and again we'll get another answer which will be slightly more accurate. And as you can see, these solutions take a little bit longer. The more nodes you have, clearly it's a bigger problem for the computer to solve. Therefore, it's going to take a little longer. So we've come down from 65 to 62 for that solution. So what you find is for frictional problems, you generally need to use quite a high number of nodes. For undrained problems, you can usually use relatively few nodes. Medium density usually works very well, but it just requires a little bit of trial and error to get a feel for the number of nodes that are required. Now, we've got here standard settings, of course, medium, fine, very fine, but you can set a custom mode, so you can actually type in as many as you want there. So if I wanted 1,240, I can have 1,240 nodes, whatever I like. So I'm going to revert that back to medium, just to give us some, so we're solving pretty quick for this demonstration. What I'm going to do is I'm going to click on this boundary here, and so anything I click on, its properties appear here. It tells me I've got one material there, which is a frictionless material. If I click on this entry here, I get this change button, and what I'm going to do is remove that frictionless material. And now, effectively, we've got a rough foundation, fully rough interface between the soil. See what that does. So that now gives us a very different collapse mechanism, and what you can immediately see is that the mechanism is hitting the edges of the boundary or domain that we've presented to the software. These are probably not real boundaries. They're artificial there just to give us a domain that the computer can solve, but in effect we've probably got a semi-infinite domain. So if we see something like that, we need to make sure that the mechanism does not intersect these kind of artificial boundaries. So we need to move these boundaries out. So again, if I click on a boundary, its properties appear up here, but in geometry appears down here. So at the moment this boundary is located at coordinates 1.750 to 1.751. What I'm going to do is type those in and increase that. I'm going to double the extent of that boundary. I'll do the same on the left hand side. And I'm actually going to drop the boundary down a little bit as well. So I just have to know in advance that this will be sufficient to give us a solution that will be contained in the boundaries. So now we get the full mechanism appearing, and we haven't got interference from the boundaries, so that's not going to affect the solution. And we get the answer for a rough footing, and the load capacity has gone up quite significantly compared to the smooth footing, which is what we expect. So that's a very brief kind of overview, just exploring the software using the simple case of a simple footing. We've looked at undrained soils, we've looked at drained soils, we looked at the boundary, we looked at how it solves a problem with nodes and slip lines. Last thing, very quickly, is we can put water into the problem. There are various ways of doing that. I haven't got time to cover all of those in this introduction, but simplest way is to click on this button here. This is draw the water table. I could draw a water table across the problem like this. Now have a water table and then solve the problem again, and we'll now got a solution. Which incorporates a water table and modifies the solution. Yeah, apologies for that. Seems to have. Occasionally we get what's called a slow progress. This is we're using a third-party linear programming solver, and occasionally it throws up a slow progress, which means that it's got kind of stuck finding the linear programming solution. Often if you resolve, it just gives you the answer straight away. But in this case, you can see now I've got a solution where we've got the water table is affecting the lower part of the mechanism here. Because the water table's inclined slightly, the mechanism has skewed itself to the right to make use of that weaker soil where the water is, and the adequacy factor has gone down from the previous case, which was about 170, or sorry, 140, I think, if you scroll up, 147. So that water has reduced the bearing capacity as we would expect. Now, we're not restricted to solving bearing capacity problems. As you've seen earlier, we can solve any geometry. I'm just going to move to a slope stability problem. Again, we have a wizard that generates the geometry. I'm going to stick with the defaults. So we get a very steep slope here. This is an undrained problem. And what I want to emphasize here is this setting here. We have a choice here of factor load or factor strength. So factor load says basically ask the software how much bigger does an applied load have to be to cause collapse. That's very relevant for, say, bearing capacity problems. Factor strength is more relevant for slopes. So what we want to know is how much do we have to reduce the strength of the soil by to get to collapse. So I click solve here. Software will run through quickly run through a range of mechanisms and finds the critical mechanism. Says basically we have to reduce the strength of the soil in the problem by a factor of 2.47, and we'll get this failure mode in the slope. Just to clarify that, if I click on this material, this body here, I can see the soil. We're using soil A. It's got an undrained strength of 50. If I change that to 25, so I reduce the strength and resolve, then we should find that my factor of strength should halve as well. And so I need to reduce it by a factor now of 1.23 to cause collapse, which is what we'd expect. So that's half the value we had before. I'll just undo, so that should revert the strength back to 50. The other way to, or you can also add other loads. So here we could add a load of, say, 100 on the surface and solve again. So we can have surface loads, self-weighted materials, and now with that surface load, we've got an adequacy of strength of 0.91. As soon as it goes below 1, that means it's not safe. It basically means you've got to divide that strength by 0.9, effectively multiply it by 1.1 for it just to be on the point of collapse. So at the moment it's overloaded, it's unstable, and that's because we've added in that load there. So it's very flexible in terms of changing around that. Now, that's a factor of safety on strength. What I can do is I can flip to factor load and ask the software, well, how big does this load on the surface have to be to cause collapse? In order to do that, I need to set a setting here called adequacy true, and that's for me to tell the software that I want it to find the number I have to multiply that load of 100 by to cause collapse. I've also set that true on the self-weight of the soil. I'm going to set that to false. So we're simply asking the software, what do I have to multiply that surface load by to cause collapse? And I get an answer here of 0.86. It's different from the previous case. And so this load is too big. It would need to be 86 roughly to cause collapse in this particular case. Now, we have a feature here called Diagnostics, which if you click, it gives you some background information to the problem. So here we can see it tells us I've got this adequacy factor applied to one boundary load, and I'm hyperlinked to the load that I want to see. It tells me what sort of loading types have been applied. This is down to partial factoring, which we'll talk about later. And it's told me materials are set to undrain and so on. This is a fairly simple problem, but this is a very useful feature of the software, which allows you to give you a quick overview of the whole problem. So once you've set it up, just to check that it is as you expected or as you planned to set it up. What we can also do in a problem like this is, if I run that, you'll see the sort of mechanism we're getting goes down to the toe. If, for example, in a slope we might have a pre-existing slip surface, I'll do this very simply, but I can use this drawing tool. Allows me to draw boundaries. This blue button on the left is draw a line. That allows me to put a line in there, and I can assign, for example, a very soft clay to that boundary. So effectively I've got a very weak interface here, which is weaker than the surrounding soil. If I click Solve, the software then says now I can find a collapse mechanism which utilizes that thin slope. It'll give me a lower adequacy factor, and so just press the wrong button there. We can add in things like pre-existing slip surfaces, etc., or thin layers of different properties. So these boundaries can be inside a soil body, or we can use these on the interface between, say, a foundation and a soil, as we saw before. Okay, that's a slope. We'll have a quick look at another problem type. So we'll have a look at a gravity wall. Again, I'm just going to accept all the defaults. So basically we've got a wall here with a soil behind it. Soil, again, undrained, shear strength of 50. Underlying soil here is same strength. And just show you this well, if I go preview nodes, what we've done here, what the software's done here is it's put more nodes at the base than behind the wall. So if we're expecting a more complex mechanism below the foundation, then we might put more nodes there just to capture that accuracy. So it is possible to vary the nodal densities in each body, and that's basically tuned by these numbers here. So you can see that if I select here, we've got these spaced at 1/2. If I click here, they're spaced at 1, or relative spacing of 1. So if I click Solve, click Solve. In this particular case, the mechanism actually ignores the underlying soil and just slides on the surface. But if the underlying soil here, supposing I reduce its strength to 30, we should get a failure including the underlying area. In this particular case, it's actually turned out to be a relatively simple mechanism underneath the wall, so maybe we didn't need all those nodes, but in other scenarios you can get more complicated mechanisms, particularly where the wall is undergoing more of a bearing capacity failure. I've just reverted back to the original strength, so if I click Solve here, what I want to show is that when we get the solution, if we want to report about that, we can click Report here, and that produces a document which you can edit with all the background to the project, all the details that you've entered, image of the collapse mechanism. If you want, it can give you all the coordinates of the boundaries and the geometry, details about the water table, the materials that are used in the problem, partial factors that are used. We'll come to that later. And again, if you wish, it can also give you free body diagrams for each of the elements of the block, so that if you wanted to check you can, for a very simple mechanism, you can check that by hand if you wished, just to see what's going on. That can be useful occasionally if you get a mechanism which you're not quite sure why that's being produced by the software. Getting the numbers and having a look at those can usually make sense of those things. You can also click on blocks. Sorry, just saw that. You can also click on the blocks and get distributions of forces or the forces acting on each block from the diagram. And again, you can check that equilibrium in that way. We'll have a quick look at another problem. So let's look at a stem wall. So this is a problem where the weight of the soil itself is providing some of the stability of the wall. And in this particular case, it's quite convenient to actually separate out these triangular areas, these corners within the soil body, because generally these don't deform, so it gives the software the bit more flexibility to treat the soil and the wall as a single mass. Now what I wanted to do here was just give an example of if you wanted to import a geometry. We can use DXF. What I'm going to do here is actually export this geometry and then regenerate it. So if I have an export here, I can export this geometry as a DXF file. I'll call that stem wall. And then if I want to start a new project, start an empty project, finish that, turn off the grid. But I can import a geometry, this stem wall, as a DXF file. So we generate a DXF file, but we can use any DXF file from a CAD program, whatever you like, and we get the bare bones geometry there. And so we can rapidly import that. Then we need to populate that with some soils. If I use the built-in soils here, I'll maybe put some backfill, firm clay, just for simplicity. Maybe some sand at the base, concrete on the wall. So now I've got all the soil types there. I also need to set boundary conditions. I can do these collectively if I click on several at once. I can set all the properties there in one go, fixed. I also need to do the back at this stage. And perhaps I'll apply a load to the surface of a unit load and put adequacy true. So that's generated that problem very quickly. If I click solve, hopefully we get a failing mechanism. So the wall is sliding, tilting slightly, and it's very strong. We need to multiply that surface load by 206 to get collapse. And again, if we wanted to look at these diagnostics, it tells us a bit more information in this particular problem. We've got adequacy on one boundary. It also gives us advice such as the following interfaces, which are basically around the stem wall, separate a strong material from a weak material. And it's just telling us that maybe we wanted to specify the interface properties. At the moment, the software is modeling that as a fully rough interface. Maybe we wanted something slightly different. And again, it gives us some information about the materials we've set. This diagnostics also come up if we forget to put a load on. So, for example, if I just put a fixed load here and I haven't applied adequacy to anything, then the software will tell me I need to set an adequacy factor. I need to ask the software how much bigger do I have to multiply something in this problem by to cause collapse. Okay, so that's a stem wall. We'll have a look at one last problem type, which is a sheet pile wall. So here we have a sheet wall, and we've basically, again, we've got clay, for the moment we've got clay at the back. This is set to be always undrained, so it's got an undrained strength of 20, and this material is also always undrained, strength of 25. I'll just click solve for the moment, and what we've done here is we've actually put an adequacy factor true on the weight of this soil. So in this particular problem, we're just saying how much heavier does this soil here have to be to cause collapse. So we can cast the problem in many different ways depending on what we're interested in. So the software finds a collapse mechanism. If I animate it, what you see is actually we get a tension crack opening up between the wall and the soil, and most of the pressure is down here. And for a retaining wall, the way it's modelled, we can generate bending moment diagrams, pardon me, and also get axial force and shear force in the wall as we go. So just to explain in a bit more detail, this element here is actually modelled as what we call an engineered element. I haven't got time to describe that in detail, but essentially for a sheet pile, it allows us to specify a bending moment within it. Some other numbers which are generally set to infinity for a sheet pile wall. This is the key number, and also we have boundary materials on the left and on the right. So you can see that we've actually modelled this with frictionless interface and the tension cutoff. So that tension cutoff material is the key material which allows us to model that tension crack. I can actually remove that, so I'm going to remove that from both sides of this wall and rerun the model, and you'll see that when we do that, because it isn't allowed to form a tension crack, we get a different collapse mechanism, a very simple collapse mechanism, which is just very simple sliding across the wall and a very different bending moment distribution. So we've got significant flexibility in modeling interfaces. I'm just going to revert those two changes, so I think we're back to those two materials. And I'll get rid of that tension crack. In other words, suppose we wanted to retain sand, so I'm going to replace that with sand, and we'll look at the problem. We get a different mechanism here. Clearly you're not going to get a tension crack between a dry sand and a retaining wall, and now the wall is going to rotate. And again, this green graph here basically plots the bending moments. We can change that by right-clicking. We can plot different values, but we're most interested in bending moment in this particular case. We can see the biggest bending moment at the moment, that if we hover here, is roughly 48.5. Now you can use the software to actually check to see whether you're going to exceed bending moment. There, the software is telling us that the maximum bending moment gets up to about 45, but it's better to actually set the actual bending moment to a value and allow the software to find the collapse mechanism that involves that. So if I set that bending moment to 40, what we should find is that a plastic hinge forms, and yeah, it does there, and we get a different, similar bending moment distribution, but a very different mechanism. So basically the wall hinges at this point, and we've limited to this bending moment of 40. So it's better to do that, is to actually set the bending moment in the software to the value you want to use, and get the software to find the critical collapse mechanism that involves that, rather than interpreting this curve if you're not getting yielding in the wall. Okay, so that's very briefly looking at modeling tension cracks and a retaining wall, and just to finish off, we're going to have a look at how the software deals with partial factors. So we're going to go back to the original simple footing problem, and I'm going to set a load of 100 here. So I click on that. What you see is we have permanent, variable, and accidental loads, so I can set different load types. So these correspond to the Eurocode type designations. If you don't use Eurocode, then These give you the flexibility to model a range of different load types and apply partial factors to those. So it isn't restricted to Eurocode, but it's definitely designed around the Eurocode kind of terminology. So what I've done is I've set that load to 100, adequacy factor of true, which means the software will say how much bigger does that load have to be to cause collapse, and it will calculate that. Now if I click on this scenario manager, what appears is a set of factors. By default it uses unity factors, so unfavorable loads are all set multiplied by 1, and we can see that this, if I cancel that, this load here, if I click on it, is defined as unfavorable, and we can set these independently. These other loads are set to 0, but the permanent load set to 100. So basically, that permanent unfavorable load will be multiplied by 1, favorable loads multiplied by 1, and the material properties are multiplied by 1. We also have this setting long and short-term analysis. This is a convenient way of switching from drained to undrained properties in the software. And what you'd have seen is that any material that I've defined, we have both drained properties and undrained, and the ones the software uses are defined by this setting here. So if we say always undrained, it will always use that CU of 50. If I say always drained, it will always use C dash of 0, phi dash of 30. And if I say drained or undrained, then the choice of which one it uses is defined by this flag here, long-term analysis, false or true, which is also duplicated in the scenario manager. So clicking true here means it will always use the drain parameters where it has the choice. Turning it off means it will also use undrained. What I'm going to do here is just set up some multiple scenarios. So what we might want to do is check this problem with Eurocode 7 Design Approach 1 Combination 1 and Combination 2. And you can see that in this case, combination 1, we're going to multiply that permanent and favorable load by 1.35, but we're not going to factor the material properties. These are all factored by 1. And in scenario 2, the material properties are going to be factored, but the permanent load is not going to be factored. And the software will basically solve the problem twice with those different sets of factors. If I click Solve, you can see down here we've got some tabs, scenario 1, scenario 2. Both cases, the mechanism turns out to be the same. It's only really for frictional materials when we factor the strengths that we would expect to see significant changes in the mechanism. And you can see that we've got an adequacy factor here of 1.927. So that's effectively the over-design factor over and above the Eurocode factors on this problem. So having applied the Eurocode factors, we've got an extra margin of 1.9 over and above that on that load. And for Design Approach 1 Combination 2, we've got a slightly lower factor, which is what we expect, because we're factoring the strength of the soil down by 1.4 in this case. We're factoring the load up by 1.35 in this case, and for an undrained problem, there's a linear relationship between the strength and the load, so this is the more critical case, as you'd expect. So essentially, when you're using partial factors, for example with the Eurocode, as long as the adequacy factor is bigger than 1, you've satisfied the criteria. If it's less than 1, then you haven't satisfied the criteria and you're going to need to do something to the definition of the problem, strengthen the soil somewhere or reduce the loads or whatever in order to improve that. Okay, that I think takes me close to being out of time, so we've run through the software. What I'm going to do is just wrap up by just recapping very quickly on what I've said there. Key thing about this software, we're doing ultimate limit state analysis, and it requires a slightly different sort of way of thinking about the problem that you may not be used to with conventional analysis, but once you've got the hang of it, it's very quick and easy to do. But as you've seen as I've gone through these issues, what we can say is anything we design we hope is going to be inherently stable, nowhere near its ultimate limit state. If we're doing an ultimate limit state analysis, we have to drive the system to collapse by some means. We can do this implicitly or explicitly. In many conventional analyses and textbooks that you come across, It's been done implicitly, whereas when using numerical analysis, you have to do this explicitly. And we've seen that with the software. Two basic ways of doing that. First way is how much bigger does a load in the system have to be to cause collapse? Or in this particular case, by what factor A does the load need to be increased to cause collapse? That gives us an adequacy factor on load, which may be the same as a factor of safety of load in the kind of conventional sense. Or alternatively, we can ask the question, how much do we have to reduce the strength of the soil by in order to cause collapse? And again, that's an adequacy factor on strength, and that again may be a factor of safety on strength for the problem. And if the adequacy factor is bigger than 1, the system's stable. If it's less than 1, it's unstable. If you've applied partial factors, for example, in the Eurocode or any other code in advance, then if it's bigger than 1, you've complied. If it's less than 1, you haven't complied with those factors. So, I hope that's given you a useful introduction to the software, give you a feel for what it can do, how it can be used. I haven't had time to cover every item, but hopefully you've seen it's a very interactive tool. It solves quickly, allows you to change the problem interactively, answer what-if type questions, get a good feel for the problem. We can deal with any ultimate limit state problem type. There's no need to put in idealizations or correction factors for non-standard geometries. You can solve slopes, foundations, retaining walls, whatever you can draw, essentially, you can formulate as an ultimate limit state problem. And a lot of our users use it to do parametric studies, so that if you want to run through a whole set of different variants on properties, you can run that very quickly through that and get a good feel for how the parameters change the nature of the interaction. So that kind of wraps up where we are. We now move to the questions session, so I'll see if we've got any questions. See if any come up. Okay, I have a question. Can I model soil reinforcement such as soil nails or geotextiles? The answer is yes. Essentially, I can use a wizard here with, for example, this is a reinforced earth wall using reinforcement strips here. This uses the same engineered element that we use for a sheet pile, and by changing the numbers in some of the parameters there, haven't got time to go into that in detail, you can basically set this one-dimensional element to model a sheet pile wall or a reinforcement strip or a soil nail or some geotextile. So in this case, these are reinforcing strips anchoring panels, concrete panels. So I click solve here. The software works out the reinforcing effect of those strips, its ability to transmit tensile forces through the soil from one area to another. And in this case, the software will actually plot by default the axial force along the reinforcing strip, so you can see how that's built up over its length. Another question, can I incorporate seismic loading? Yeah, we can do that. So again, I'll perhaps go to a slope problem. We can apply seismic actions using pseudostatic approach. So here we've got a button which allows us to apply horizontal or vertical accelerations, and we can apply them in two ways. We can either apply them as a fixed acceleration, or we can actually ask the software what level of acceleration do we require to cause collapse. So for example here, if I set this to 1, but I've got adequacy true, and if I remove adequacy from the weight of the soil, what the software will do is it will tell me what do I have to multiply this unit horizontal acceleration by to cause collapse due to lateral acceleration. So if I click, okay, it's giving me a little warning, which I'm in factor strength mode. I actually want, for this particular case, I want to be in factor load mode. I'm going to stop that solution, flip to factor load. So what this will do is if I click solve, it'll tell me effectively what does the horizontal acceleration have to be to cause collapse. And here it actually turns out to be 1, so this problem requires 1g horizontal acceleration to cause collapse, which is pretty high, but that's fully driven by lateral body forces rather than vertical ones. I think we're close to running out of time, so I'm going to pass you back to Tom to wrap up the presentation. So thank you very much for listening. I hope you've got a good feel for how the software works and what it can do. If you have any other questions, do feel free to email them through.
Thank you, Colin, and thanks everyone for listening. As we mentioned at the beginning of the session, for people who are current users of the software, we obviously hope you learned something new about it, and if it's prompted any questions, please do get in touch via the telephone or support@limitstate.com, and we'll be happy to help you there. For those of you who aren't current users of Limit State Geo, we will be in touch over the next few days just to get some feedback about the webinar, find out if you have any further questions and whether you think Limit State Geo will be useful to you. Everyone may also be interested to know that we do have a number of forthcoming webinars covering all the Limit State product range. So as Colin showed at the beginning, some of the Masonry Arch and the slab analysis software, and these will focus on particular problem types and applications. So there will be some Limit State Geo ones that deal with some of the aspects that Colin's covered today in more depth. So please do look out for these event notifications that will be sent out via email and posted on our website, which is www.limitstate.com/events. So again, thank you all for listening and taking the time to join us this morning. We hope to see you all again soon for one of the future sessions. Goodbye.